When you visit Flagstaff, Arizona, Lowell Observatory is a must-see. To get there, you'll drive west along Santa Fe Avenue from downtown until you get to Mars Hill Road. At that point, you'll notice a sudden increase in slope, followed by a couple of switchbacks until you reach the top of Observatory Mesa. Why is that? Because you've just driven up the front of a gigantic lava flow erupted from the A1 mountain vent northwest of Flagstaff approximately 330,000 years ago. My interest in Observatory Mesa was piqued when I learned that excavation for the new Astronomy Discovery Center would reveal fresh exposures of the top of this ancient lava flow.
Holy cow!
That's the first time I've seen this.
That was a good one.
At first glance, the face of the exposure revealed well-developed soil horizons and a buried stream channel, but the bedrock was a confusing mess. Upon close examination, I realized that flow banding in the lava was randomly oriented, indicating that these must actually be large broken blocks separated by soil development. Several distinctive patches of the exposed face ranged from black to bright red in color, in contrast to the dark gray of the cooled lava blocks. I thought at first that these might have formed from the corrosive effects of escaping volcanic gases. Dr. Nancy Riggs, a volcanologist at Northern Arizona University, wasn't happy with that idea, and proposed instead that these were also blocks, but blocks of the A1 mountain volcano that had tumbled down onto the top of the lava flow, rather than cooled lava. Close examination revealed layers of cinders and other rock fragments typical of A1 mountain in several of these blocks, strongly supporting Nancy's interpretation. So what we have here is a mantle of rubble on the top of what was essentially a lava conveyor belt oozing 3 miles to the southeast from its source vent. The blocky nature of the top of the flow couldn't be determined from the test drilling done before construction started. More work than anticipated was required for prepping the foundation of the building, leading to a cost overrun. Understanding geology, as usual, is of practical importance. From a strictly scientific standpoint, my big question is, how exactly do you get a lava flow like this one? The Observatory Mesa lava flow covers 10 square miles and averages 250 feet thick. The total volume of material erupted is 2.5 times that of Sunset Crater. Somehow, the lava was viscous enough to maintain such a great thickness, yet fluid enough to flow for 3 miles. The measured viscosities of modern lava flows vary over 8 orders of magnitude. Near the vent on Kilauea, the USGS has measured flow velocities of more than 15 miles an hour for very hot basaltic lava. As these lavas cool, there is commonly an abrupt transition to what are called ah flows that may creep along at feet per hour. Luce, a company in Italy, has digitized and posted astonishing archival footage from an eruption of Mount Etna in 1928. In the footage, you can see an ah flow slowly advance into a train station. The movement is so slow, the railroad workers have time to load rails onto a flat car and move them out of harm's way. Lavas high in silica are extremely viscous right out of the vent and rarely flow for great distances. Right here in Flagstaff, one of the lava flows erupted from Mount Eldon was so viscous it didn't even make it to the base of the mountain before it cooled and solidified. So what do we know about the Observatory Mesa flow that can explain its unusual history? Could it be a function of lava chemistry? First off, the Observatory Mesa lava flow is not basalt. It's composed of a rock called benmarite, which is a type of tracheandesite with a lot more sodium than potassium in it. Benmarites are much less common than basalts, but they are globally distributed. From background reading I've done, it seems benmarite magmas are largely produced from basaltic magma by the process of fractional crystallization. From 1912 to 1937, the petrologist N.L. Bowen conducted a series of experiments that demonstrated that as magmas cool, the first minerals to crystallize contain more iron, magnesium, and calcium, and less silica, sodium, and potassium than the parent magma. If these minerals settle out, the liquid that's left will be higher in silica, potassium, and sodium, and lower in iron and magnesium and calcium. Bowen called this process fractional crystallization and provided the first coherent explanation for why the Earth has different types of magma. From what I've read, if you start with an alkali basalt magma, it's straightforward to produce a benmarite magma via fractional crystallization. So, do we have video of modern eruptions of benmarite lava that we can compare to Observatory Mesa? The one modern example I've been able to find is the 2010 eruption of Eyjafjallajökull in Iceland. This eruption produced a broad range of volcanic activity, but at no point produced a lava flow 250 feet thick, covering 10 square miles. So if magma chemistry isn't the answer, what other factors can influence lava viscosity? A striking feature of the benmarite blocks is how little vesiculation most of them exhibit. According to the San Diego State website, How Volcanoes Work, reduced gas content will increase the viscosity of a lava flow, and that may be the case here. In contrast to the Sunset Crater eruption, in which a relatively bubbly magma triggered at least half a dozen subplinian eruptions and pervasive strombolian activity, the A1 mountain cinder cone is relatively small compared to the Observatory Mesa lava flow. Of course, the next logical question is, why was this magma relatively low in gas content? I have yet to find an answer. As usual, thinking you've answered one question just leads to another one. Of more general interest, could an eruption like this take place in the future within the San Francisco Peaks volcanic field? Obviously, the answer is yes, although statistically the odds are much higher of a Sunset Crater-style eruption. In 10, 20, 30,000 years from now, this landscape will look dramatically different than it does today.